ARM uses a RISC instruction set architecture.
ARM uses a RISC instruction set architecture.
The core supports both ARM and Thumb instruction sets.
The core supports both ARM and Thumb instruction sets.
ARMv8 introduced 64-bit architecture support.
ARMv8 introduced 64-bit architecture support.
We're implementing ARMv9 security features.
We're implementing ARMv9 security features.
The instruction decoder handles variable length instructions.
The instruction decoder handles variable length instructions.
ARM cores are optimized for power efficiency.
ARM cores are optimized for power efficiency.
The pipeline depth is 13 stages in Cortex-A78.
The pipeline depth is 13 stages in Cortex-A78.
We're using big, little architecture for heterogeneous computing.
We're using big, little architecture for heterogeneous computing.
The execute stage includes multiple ALUs.
The execute stage includes multiple ALUs.
ARM Neon enables SIMD vector processing.
ARM Neon enables SIMD vector processing.
SVE2 provides scalable vector extensions.
SVE2 provides scalable vector extensions.
The core supports out-of-order execution.
The core supports out-of-order execution.
Branch prediction accuracy exceeds 95%.
Branch prediction accuracy exceeds 95%.
We're implementing pointer authentication for security.
We're implementing pointer authentication for security.
The instruction fetch bandwidth is 16 bytes per cycle.
The instruction fetch bandwidth is 16 bytes per cycle.
ARM TrustZone provides hardware isolation.
ARM TrustZone provides hardware isolation.
The core has separate integer and floating point pipelines.
The core has separate integer and floating point pipelines.
We're optimizing for mobile workloads.
We're optimizing for mobile workloads.
The microarchitecture supports speculative execution.
The microarchitecture supports speculative execution.
ARM cores scale from Cortex-A5 to Cortex-X series.
ARM cores scale from Cortex-A5 to Cortex-X series.
The core achieves 4.0 IPC on integer workloads.
The core achieves 4.0 IPC on integer workloads.
Power efficiency is measured in performance per watt.
Power efficiency is measured in performance per watt.
We're implementing dynamic voltage and frequency scaling.
We're implementing dynamic voltage and frequency scaling.
The big cores handle performance-intensive tasks.
The big cores handle performance-intensive tasks.
Little cores optimize for power efficiency.
Little cores optimize for power efficiency.
DynamIQ enables flexible core clustering.
DynamIQ enables flexible core clustering.
The performance governor adjusts frequency based on load.
The performance governor adjusts frequency based on load.
We need to balance single-thread and multi-thread performance.
We need to balance single-thread and multi-thread performance.
Thermal throttling limits sustained performance.
Thermal throttling limits sustained performance.
The core power state transitions are optimized.
The core power state transitions are optimized.
We're targeting 5 WTDP for mobile applications.
We're targeting 5 WTDP for mobile applications.
Race to sleep strategy minimizes energy consumption.
Race to sleep strategy minimizes energy consumption.
The heterogeneous scheduler assigns tasks efficiently.
The heterogeneous scheduler assigns tasks efficiently.
Peak performance is 3.0 GHz on performance cores.
Peak performance is 3.0 GHz on performance cores.
Idle power consumption is below 100 milliwatts.
Idle power consumption is below 100 milliwatts.
We're implementing aggressive clock gating.
We're implementing aggressive clock gating.
The power delivery network handles peak current demands.
The power delivery network handles peak current demands.
Performance per area is a key design metric.
Performance per area is a key design metric.
We need to optimize for benchmark scores.
We need to optimize for benchmark scores.
Battery life depends on workload characteristics.
Battery life depends on workload characteristics.
The L1 cache is 64 kilobytes per core.
The L1 cache is 64 KB per core.
We're using a 3-level cache hierarchy.
We're using a 3-level cache hierarchy.
The L2 cache is shared among core clusters.
The L2 cache is shared among core clusters.
Cache coherency is maintained by AMBA-Chi protocol.
Cache coherency is maintained by AMBA-Chi protocol.
The TLB has 256 entries for address translation.
The TLB has 256 entries for address translation.
We need to optimize cache replacement policy.
We need to optimize cache replacement policy.
Prefetching improves memory access patterns.
Prefetching improves memory access patterns.
The memory controller supports LPDDR5 at 6400 Mount s.
The memory controller supports LPDDR5 at 6400 MTS.
Cache line size is 64 bytes.
Cache line size is 64 bytes.
We're implementing exclusive cache hierarchy.
We're implementing exclusive cache hierarchy.
The system cache improves GPU-CPU communication.
The system cache improves GPU-CPU communication.
Memory bandwidth is 51.2 GB per second per channel.
Memory bandwidth is 51.2 GB per second per channel.
We need to reduce cache miss latency.
We need to reduce cache miss latency.
The write buffer coalesces multiple stores.
The write buffer coalesces multiple stores.
Cache partitioning prevents interference.
Cache partitioning prevents interference.
The Society integrates CPU, GPU, and NPU.
The SOCA integrates CPU, GPU, and NPU.
We're using AMBA AXI for interconnect.
We're using AMBA AXI for interconnect.
The ISP processes camera data in real time.
The ISP processes camera data in real time.
The modem supports 5G connectivity.
The modem supports 5G connectivity.
We need to optimize for thermal constraints.
We need to optimize for thermal constraints.
The display controller drives 4K at 120 Hz.
The display controller drives 4K at 120 Hz.
Video codec accelerators handle H.265 encoding.
Video codec accelerators handle H.265 encoding.
The NPU delivers 6 TOPS for AI workloads.
The NPU delivers 6 TOPS for AI workloads.
We're integrating a dedicated security processor.
We're integrating a dedicated security processor.
The audio DSP handles low latency processing.
The audio DSP handles low latency processing.
Power management IC coordinates voltage domains.
Power management IC coordinates voltage domains.
The Society is manufactured on 5 nanometers process.
The SOCA is manufactured on 5 nanometers process.
We need to optimize die area and cost.
We need to optimize die area and cost.
The package uses advanced flip chip technology.
The package uses advanced flip chip technology.
System-level validation includes real devices.
System-level validation includes real devices.
The core is compatible with ARM compilers.
The core is compatible with ARM compilers.
We're optimizing for Android runtime performance.
We're optimizing for Android runtime performance.
The instruction set supports hardware virtualization.
The instruction set supports hardware virtualization.
ARMv8 crypto extensions accelerate encryption.
ARMv8 crypto extensions accelerate encryption.
We need to ensure Linux kernel compatibility.
We need to ensure Linux kernel compatibility.
The debug architecture supports core site trace.
The debug architecture supports core site trace.
Performance monitoring counters track microarchitectural events.
Performance monitoring counters track microarchitectural events.
We're validating with ARM Architecture Compliance Suite.
We're validating with ARM Architecture Compliance Suite.
The toolchain includes GCC and LLVM support.
The toolchain includes GCC and LLVM support.
Binary compatibility is maintained across generations.
Binary compatibility is maintained across generations.
We need to optimize for common software frameworks.
We need to optimize for common software frameworks.
The platform supports trusted firmware.
The platform supports trusted firmware.
Machine learning frameworks leverage Neon instructions.
Machine learning frameworks leverage Neon instructions.
We're implementing ARM Scalable Matrix Extension.
We're implementing ARM Scalable Matrix Extension.
The ecosystem includes extensive software libraries.
The ecosystem includes extensive software libraries.
We're running ARM architecture tests.
We're running ARM architecture tests.
Silicon Bring Up starts with JTAG debug.
Silicon Bring Up starts with JTAG debug.
The first boot sequence was successful.
The first boot sequence was successful.
We need to validate cache coherency protocols.
We need to validate cache coherency protocols.
Performance validation uses spec CPU benchmarks.
Performance validation uses spec CPU benchmarks.
The core passed all functional tests.
The core passed all functional tests.
We're debugging a corner case in branch prediction.
We're debugging a corner case in branch prediction.
Power measurements match pre-silicon estimates.
Power measurements match pre-silicon estimates.
Thermal simulation guides cooling solution design.
Thermal simulation guides cooling solution design.
We're characterizing performance across voltage corners.
We're characterizing performance across voltage corners.
The validation plan covers all operating modes.
The validation plan covers all operating modes.
We need to fix a race condition in the load store unit.
We need to fix a race condition in the load store unit.
Post-silicon tuning optimized frequency by 10%.
Post-silicon tuning optimized frequency by 10%.
The core meets all performance targets.
The core meets all performance targets.
Production qualification is complete.
Production qualification is complete.